In this video, we're going to examine why the non-relativistic velocity addition formula breaks down. So as you recall, we've introduced the equation Vxz equals Vxy plus Vyz, meaning if we know the velocity of x relative to y and we know the velocity of y relative to z, then when we add them together, we can find the velocity of x relative to z. And we've talked about examples of Alice throwing a ball on the train and the train moving relative to the ground, and we can use that to find the speed of the ball relative to the ground. But we know that this equation only works at low speeds, and that it fails at high speeds, and you've seen examples of why that is, or maybe you've thought of your own.
And just to make sure we're all on the same page, let's say that instead of Alice throwing the ball a few miles an hour, Alice can throw the ball relative to the train at half the speed of light, and that the train is moving relative to the ground at 3/4 of the speed of light. According to the equation above, the velocity of the ball relative to the ground would be the sum of those two, v ball train plus v train ground is half c plus 3/4 c. Well, that's 1.25 times the speed of light. And we know that that cannot be, because even though you may not have taken a course on relativity, you likely have heard that there's an ultimate speed limit in the universe, that nothing can travel faster than the speed of light. So this is a nonsensical result. And we got to that nonsensical result using this non-relativistic velocity addition formula. So that suggests that there's something wrong with the formula.
But why is it that this equation breaks down? I mean, it seems so straightforward. It seems so common sense, right? The velocity of the ball and the velocity of the train add together to give you the velocity of the ball relative to the ground. So where's the flaw in the logic? So we'll come back to our previous example where we have Alice on the train throwing a ball and the train moving relative to the ground, and we have labels for these velocities. Okay, so we have the velocity of the train relative to the ground, VTG, written out here, and we want to know what is the velocity of the ball relative to the ground, VBG, and we know from our general equation that that velocity can be expressed as the sum of the ball relative to the train and the train relative to the ground. So let's just give ourselves some actual numbers here. Let's assume that Alice can throw the ball at 3 meters per second. These are the numbers we used before, I believe. And that the train is moving at 21 meters per second relative to the ground. Okay, and what we had found last time was that the ball relative to the train, that was a 3 meters per second, plus the train relative to the ground, 21 meters per second, sum together to give you a whopping 24 meters per second for the ball speed relative to the ground. Okay, and again, very straightforward. We've seen this calculation before. It matches your intuition and common sense. And yet, we know that this procedure does not work at high speeds. So the question is why? What's wrong in the logic? Why does this not work in general? So to do this, we're going to actually write out, using like in paragraph form, this equation, right? So rather than looking at it symbolically with math, we're going to spell out what each of the terms mean. And in doing so, we're going to figure out where the flaw in the logic is, or where the problem lies, and why this problem only appears at very high speed. So here I've written out the equation in a kind of verbose way in the specific case of the ball and the train. So in each second, the ball gets 3 meters closer to the front of the train, 3 meters per second. Likewise, in 1 second, the train itself moves 21 meters further to the right on the page. Therefore, in 1 second, the ball gets 24 meters further to the right on the page. The 3 that it gains on the train and the additional 21 that the train gains on the track. So this all seems very good and sensible. So pause the video for a moment, think about this, and try to identify where the flaw in this logic is. Or what is the hidden assumption in this statement? Were you able to get it? The implicit assumption here is that the clock on the train and the clock on the track or on the ground are equivalent to each other. In other words, 1 second of train time is the same as 1 second of track time. And while that is kind of our daily experience, that all clocks are the same and there is one universal time, it turns out that the faster and faster you go, the more and more incorrect that statement becomes. And we'll explore this in much more detail throughout the course, but time is a relative concept. There's no absolute time. So what I've done here is written out the same paragraph, but been explicit about when we're talking about train time and when we're talking about track time. So we see in each second of train time, the ball gets 3 meters closer to the front of the train. In 1 second of track time, the train itself moves 21 meters further to the right on the page. And now that I've inserted explicitly when we're talking about train time and when we're talking about track time or ground time, we see that that there are in fact two different clocks that we need to keep track of. And yet when we look at the second paragraph, we then say, so in 1 second, the ball gets 24 meters further to the right, 3 from the train and 3 from the track. But this in 1 second statement is the dangerous one. Okay, well, are we talking about track time or train time? And it appears that we're mixing the two. Indeed, this statement in 1 second is incorporating both train time and track time. So we're not actually able to distinguish track time from train time here because we've lumped them together. And now that we know that the clock on the train and the clock on the track are different, we see where the problem lies. The problem is that we're trying to merge both track time and train time together in this statement of in 1 second. And that's where the flaw in the logic lies. We're not allowed to combine train time quantities and track time quantities, and yet that's exactly what we've tried to do. We've combined quantities that involve track time with quantities that involve train time with a simple addition, and what we're going to see later in the course is that just isn't valid. Well, so now we know why there's a problem. The question is, how do you remedy that problem? So we will learn how to combine velocities when objects are moving at high speeds. We won't do that right away. We're going to do that later in the course. For today, I just want you to understand that the non-relativistic velocity addition formula has a problem with it. And the whole point of this video is to identify what that problem was. We found what that problem was. It's a question of time. And the question then is how do we find an equation that is accurate at all speeds? And we will come to that later in the course.